Just a little bit more about me. If you don't know who I am still a licensed plumber in the state of Illinois. I was a plumbing contractor for about 11 years. And then, once you've been plumbing for so many years and you get banged up, you go to the boneyard to become an inspector. So then I became a municipal plumbing inspector for a village, and I did that for 6 years before I came to IATMO. And it was during my time as an inspector, a lot of times when you go out in the field and you're doing inspections, you got the plumbing contractor with you and you start dinging him on some code violations. Sometimes they ask you an honest question: why is that in the code? Where does that come from? Which causes the inspector to really start digging into the code and start finding the reason for the code in the first place. And I do love history, I love research, and on this topic of fixture units, I started digging, where did fixture units come from? What does it mean? How did the numbers develop? And so I stumbled upon Roy Hunter's work, and I would highly recommend, ASPE published the Hunter papers, 3 publications of Roy Hunter. Highly recommend getting those publications. They're invaluable for understanding a lot of what's in our plumbing code today. And Hunter's curve is one of those, and that's what we're going to focus on today. So I started working on this when I was a plumbing inspector, and in our state we had a problem with remodels. You have an existing home, and the homeowner wants to put in on an addition master bath. Well, how do you have to calculate the whole system again? Well, now they have an existing 3/4 water service. They put on a big master bath, and now they have to dig up their yard, pay a new connection fee, increase the water service to 1 inch, pay for a 1-inch water meter. Now the cost has just gone astronomical, thousands of dollars. So the state had to make a decision, and they said they can keep their existing water service with their new addition, when at the end of the day, after their new addition on, you go and turn on every single plumbing fixture, and if it meets the minimum residual pressure, then they don't have to upgrade. No one sizes a plumbing system assuming that every fixture is going to be on simultaneously. So that's what we're going to talk about. We started getting calls, hey, is IATMO doing anything to revise Hunter's curve for high efficiency fixtures? We're putting in these high efficiency fixtures. We know the system's oversized. Is IATMO looking into it? Yes. I put together a team of 4 of us, ASPE members, 3 ASPE members, and then a University of Cincinnati professor came on board. And for the past 5 years, we have been seeking to revise Hunter's curve. And so today, I'm going to introduce to you a calculator for estimating peak demand, a calculator that you can use instead of using Hunter's curve. But today's outline, we're going to look at the Hunter problem. We're going to look at the peak water use model, what the new code provisions are saying, and the code provisions have been balloted and approved by the Plumbing TC. So it looks pretty good as far as going into the appendix for the 2018 UPC. And then we're going to hopefully spend most of our time in the application, how to use the calculator, and then some conclusion comparisons with the way it's being done today versus using the calculator. So let's begin with the Hunter's problem. I do love talking about Hunter's curve. Years deciphering this curve, I recreated it. I understand what Hunter did, but in a snapshot, this is showing what the problem is. So back in 1940, what was a good estimate in 1940 is now an overestimate in 2017. There's really 2 factors driving the actual demand down. Well, we're using high efficiency fixtures compared to 1940 with lower flow rates. That's going to affect the curve. That's going to affect what the actual demand of a building really is. And then the p-value. The p-value is the probability of how frequently that fixture is going to be in use. Roy Hunter did not have any data, so he made some assumptions. He says, what is the worst case scenario? Well, if we have a flush valve toilet and the duration of that flush is 9 seconds, and that toilet is going to be flushed every 5 minutes, say that there's a queue of people in line that's going to be using the toilet one right after the other. That's how he derived his p-value for the toilet. 0.03 was the probability of how often that toilet's going to flush. Well, that's good if the building is under congested use all the time. What about a single-family residence? There is no congested use in a single-family residence. So how do you figure out the frequency of fixture use in a single-family residence? So that's another problem. There was a third problem that arose between last year and today. Who was at Albuquerque conference, annual conference, that saw this presentation last year? 3 people, okay, good. Well, I call this the problem of the lower boundary. How many have seen the Hunter's curve that's published in the appendix of the UPC? There's the regular curve that you're seeing here, and then there's an enlarged curve. Well, Tim Allenson published an article in Plumbing Engineer, or it might have been Plumbing Systems and Design. It was a few years ago, but he raised the question, how come those curves don't touch the line? How come they just stop? They don't go to 0. The upper curve stops at 10 fixture units, the lower curve stops at 5 fixture units. Why does it not go to 0? The real answer is this is a binomial distribution. If you've ever taken statistics, that's a familiar word. This is a binomial distribution curve, and the function of the curve does not exist, and I'll explain this. What he was doing is trying to figure out if you have a number of plumbing fixtures of the same kind, what's the probability of, out of that number of fixture units, that there will be simultaneous fixtures. Obviously not all the fixtures are going to be on simultaneous, but he was using statistics and probability. For example, if you have 6 toilets, a battery of 6 toilets, what's the probability that only 2 will be flushing at the same time? What's the probability of 3, 4? Well, then he used what's called the 99th percentile, and you'll see a graph of this a little later on, to determine the boundary, which means that, okay, I want to find, if you have 6 fixtures, what number of fixtures would be on simultaneously that would not be exceeded 99% of the time. In other words, it's a failure factor that I want to pick a number that there's only a 1% chance of that number ever being exceeded. So out of 6 flush valve toilets, only 2. And there's only a 1% chance that 3 will flush at the same time. There's even less than that for 4, maybe 0.1%. So that's really a good factor of safety. So he plotted points. In the first, well, originally, figure that these are 50, 100, 150. These are like the number of fixtures. And here, take away the gallons per minute, and this is also numbers. And so he would plot 6 out of a total number of toilets, 6, and then 2. And then he would come over, and then he would multiply 2 by the gallons per minute. So you wouldn't size the system for all 6, you would size it for 2. So now increase the flush valve toilet by a fixture unit of 10. So a flush valve toilet is fixture unit of 10. At that time, the flow rate for one flush valve toilet was 27 gallons per minute. 2 toilets, would be 54 gallons per minute. The first pointed plot is 60 and 54. So it doesn't go to 0 because you're producing a binomial curve where at least 2 are on at the same time. And then what's the point for 3? Well, how many fixtures do you have to have for 3 toilets to flush at the same time? You need 16 toilets for 3 to flush at the same time. How many for 4? 30. How many for 5? 47 toilets. How many for 6 toilets to flush at the same time? 66. So then the curve starts moving upward. So that's how he created the binomial curve. It's points. It's not even a curve. The binomial function is a discrete function. It's just a point. It's an exact amount value. And then all he did was connect the dots on the curve. And that's how he created the binomial curve. It's an equation. You plug in the numbers and you come up with an exact value of x. If you have a graphing calculator, that binomial function is in a graphing calculator. You just plug in the values and it'll tell you the exact same thing. So there's a problem with the lower boundary. So then Hunter took the curve from 60 fixture units and then he extrapolated it down to what is a fixture unit value of 1 toilet at that time was 10 at 27. So now the curve went to 1027. And that's where it stops. So if you look at the enlarged curve, it stops at 1027. The flush tank stops at 5 and 4. It does not go to 0. But it's no longer a binomial curve then. Once you extrapolate it down, it's not a binomial curve. It's an extrapolation. So I'm prefacing this because we ran into the same problem in the calculator. We had a binomial function, and when we started using it in a very small building for a single-family residence that only has a small number of fixtures in it, that formula would not work. So we had to come up with other methods to solve that lower boundary problem. It was never solved with Hunters, but we solved it. So in the 2018, both in the WESTAN and the 2018 Uniform Plumbing Code, this method is going to be published in the appendices. We're going to look at the code language, we're going to look at this calculator, and we're going to see how to use it. So here's the template of the water demand calculator. So in column A, you have a list of fixtures that are commonly seen in residential applications. In column B is where you would enter the number of plumbing fixtures actually when you're working with this. And we'll be playing with this later on. And column C is the probability of use. How frequent are these fixtures on? And D is the flow rate. And then E is the maximum recommended fixture flow rate. And this E column is what is specified in a table in the proposed code for 2018. And you'll see that there are white columns and there are blue columns. The blue columns are fixed. You can't change the blue columns. The white columns you can change, except you can't go any higher. These are for high efficiency fixtures. You can go lower if you have a fixture that has a flow rate lower than what's listed here, but you can't go higher. A good example is the task group had a real tough time with determining what is a flow rate for a bathtub. In UPC, it has a fixture unit value of 4. If you extrapolate that curve down to 0 so that you can figure out what is the flow rate of 4, it's almost a 1-to-1 ratio, so it'd be about 4 gallons. Like I said, you can go lower. 5.5 gallons per minute may be too high, but we had a statistical database of over 1,000 homes, and we evaluated all the bathtub flows in these homes. And 5.5 was about the 80th percentile of all flow rates. So it's above average. We wanted to stay on a side of safety and not under-evaluate the flow rate of a bathtub. But like I said, you can lower the flow rates, you just can't increase them in the calculator above what's listed in column E. So let's take a look at the peak water use model. There are four models or methods for estimating design flow that are built in the Excel calculator. This is Hunter's method. This is the binomial model that I was talking about. For example, if you had 20 fixtures of the same kind and the probability or the frequency of fixture use is 0.4, then this is the binomial distribution. The 99th percentile would show that there are 13 fixtures out of 20 that would flow simultaneously, and there's only a 1% chance that 14 would flow at the same time. Now this is the normal approximation to the binomial curve. Again, this is all statistics. You learn this in elementary statistics. As a side note, when I was reading the Hunter's papers, it was a bit over my head in understanding, well, he was a physicist, and understanding the mathematics, so I did go back to school. And I took geometry, trigonometry, and 3 semesters of calculus, and then I took statistics. Not because I love math, is that I was just trying to understand Roy Hunter and when I was reading his papers. So this is a normal approximation. It's a smooth curve. It's not a discrete function where there's separate points. This is a smooth curve. And it calculates the same thing. So it is a good approximation. It still will calculate 13 out of 20 fixtures in a 99th percentile. Now at the ASPE convention in 1994, Robert Wistort presented this model in an attempt to replace the use of fixture units, and I'll show you how he did it. And by the way, in the past year, I've corresponded with Robert Wistort. He's now retired, and I told him the work that we're doing, so I get this big box in the mail, and it's all of his work that he's done, his publications and everything that he did up to this 1994 ASPE symposium. So I was flattered that he entrusted me with all of his stuff. But this is what he did. He improved upon this by adding the Q value and allowing a summation of different kinds of plumbing fixtures. That's what this little sigma signifies. So now you're not looking for an X value of the number of fixtures that could be used simultaneously. You're actually calculating the flow rate at the 99th percentile directly without the use of fixture units and using a curve. So he added the Q value. So you have what you saw in the calculator template. You have the parameters right here, the N, number of fixtures, P, the probability of fixture, and Q, the fixture flow rate, and at the 99th percentile. So this is the normal equation, the normal distribution equation that will calculate the flow rate at the 99th percentile. And this is Robert's Wistort work. This was genius, and this will calculate the fixture or the demand, the flow rate demand at the 99th percentile. This model did not work well when we applied it to a single-family resident, to a dwelling. The predicted outcome was way too low, and we had to figure out why. Why was the predicted outcome way too low when we applied this model to a single-family dwelling? We had to look at what was going on in a single-family dwelling that was different than large buildings. So here's an example. This is just a very small example. Say you have 5 fixtures, and this is a binomial distribution. A Bernoulli trial in statistics means that there's only 2 possible outcomes. Either a fixture's on or it's off. So this is a binomial distribution of 5 fixtures, and what is the probability of 0 fixtures being on? What's the probability of only 1 fixture being on, etc. Here's the problem child. In single-family dwellings where there is there is not a high frequency of flow rate, you have a high probability of stagnation, of no flow. And this drives the mean flow rate down, and that's why we're getting such low outcomes using the Wist-Dort method. You don't design a building for no flow. You design a building for flow and pipe sizing for flow. So we had to do something, and this was our solution. It's called a zero truncated binomial distribution. It's a binomial distribution. We truncate the 0 probability out of the equation, and we redistribute that probability scales through the other probabilities. And this could be, so we modified the Wist-Dort method. And this is how we modified the Wist-Dort method by this P0 is the probability of stagnation. So we remove the probability of stagnation out of the equation, and now the outcomes were starting to look a little bit more reasonable. We, over 1,000 homes, we evaluated every single monitoring day, over 10,000 monitoring days, and we picked the window of observation we determined the peak time of each day. It varied in single-family homes. Some peak times were 2 o'clock in the morning. Actually, there was a peak time for each 24 hours of the day. So we evaluated the peak for each day for each home, and that's how we derived the p-value for the fixture. See these values wherever there's a P0? Put 0 for P0, and it reduces back to the Wist-Dort method for congested use. So this was a real genius. Actually, the professor of the University of Cincinnati is the one who came up with this model, and it was really good. Because you can use this model for congested or uncongested use, because when it approaches 0, when stagnation approaches 0, which means there's no stagnation, it's congested use, then all of that zeroes out, and it goes back to the Wist-Dort model. Well, there is. Whatever that P0 value is, that's built into the calculator. It will calculate a value for this P0 depending on the number of fixtures you put in the calculator and what the probability of those fixtures are. And the calculator will find the P0. You would have to have a lot of fixtures. I mean, it would have to be a huge complex of multifamily dwellings for this to reduce to no stagnation. You're going to always have some range of stagnation in a residential dwelling. So this is the second model that is built into the calculator. But again, when we applied this model to a small single-family residence, it still wasn't working right. It was acting erratically and counterintuitively as we were trying to size branches, or if the home was small. And we realized that's where we were bumping into the low boundary. The binomial doesn't work when you're going down to 5 fixtures, 4 fixtures, 3 fixtures. That binomial function doesn't work. Just like it didn't work in Hunter's curve, it didn't go to 0. Well, these normal distributions don't either. So we came up with another method. This method is used, you can use this method to come up with the 99th percentile. It's called exhaustive enumeration. This is what runs on the macros in a spreadsheet. So if you've tried downloading this water demand calculator from iAtmos site, you're going to get a Microsoft Office warning. This file has macros. It could contain viruses. Beware. That's just standard. If any spreadsheet has macros, you're going to get that warning. But the spreadsheet is safe to download. This is the only thing that runs on macros. So what this does is that whatever number of fixtures that you put in the calculator, it'll start ordering the fixtures based on all the possible number of combinations. So here we have 4 fixtures: clothes washers, dishwashers, kitchen faucets, lavatory faucets. 4 faucets. There are 16 possible combinations. It's 2 to the nth power, whatever that number is. You have 4, so it's 2 to the 4th power, 16 possible combinations. Then the calculator will order all these fixtures in order of flow rate. And then it will look for the 99th percentile, which is right here. So if these 4 fixtures were on a common branch, then the 99th percentile flow rate would be 5.5 gallons per minute. So this works on the lower boundary when you only have a few fixtures and you're trying to figure out what is the peak demand on that branch. This works quite well. This also has a limitation, because as the number of fixtures increases and it's 2 to the nth power, it starts exploding. The possible combinations start exploding exponentially. And so when you try to run the macros, you could be waiting 2 hours for it to run the full macro and then to come out with an answer. So we limited it to 30. Only 30 fixtures can work on the exhaustive enumeration. Otherwise, you'll be waiting forever for this to work. Well, then there's another method that we use. This is called Q1 and Q3. As we were working with the exhaustive enumeration, we started to discover that certain combinations always had the same demand, the 99th percentile, as the full exhaustive enumeration. So this is I don't want to say quick and dirty method, but it's pretty accurate to coincide with using exhaustive enumeration. And how this works is that you have a number of fixtures on a branch, and you order these fixtures from the flow rate from the highest to the least. A fixture with the highest flow rate is Q1, the next highest flow rate is Q2, Q3, so forth. Then all you do is you add Q1 and Q3, and that is your predicted demand for that branch. It's quick and easy, and when we compare it to the exhaustive enumeration, it's the same thing. So if you have 6 fixtures on a branch, you can order them in the order of flow rate and just sum up the Q1 and Q3, and that's your design flow rate, and it will always fall within the 95th to the 99th percentile. So those are the 4 methods that are built into the calculator. It's a lot of mathematics, a lot of statistics built in there. But that's the beauty of having a calculator. It does it all for you. You don't have to do the math. So this is just a summary of methods. This is the brains of the calculator to know which method to use. And out of respect for Roy Hunter, we call this the Hunter number, which is the sum of NP. And if that sum falls within this range, the calculator will choose this method. If it falls within its range, it'll choose this and this. And based on a scale of the building, for a small residential building, from small to intermediate, intermediate to large, and then large buildings. So these are the 4 methods built into the calculator based on the spatial scale of the building that you're estimating. And we'll take a quick look at how this got codified in the appendix of the 2018 UPC, if you haven't seen the proposal yet. The applicability, and I'll try not to just read all of these, but the applicability is for residential applications only with high efficiency fixtures. This isn't applicable for commercial applications, just for residential. And here again, it's pointing out the water conserving fixtures, what the design flow rate is, that using this calculator, you cannot exceed these design flow rates. Like I said before, you can go lower, but you can't exceed these design flow rates. The water calculator is downloadable. You do have to download the Excel spreadsheet. The meter in a building supply, and we'll be doing this, you just enter in the number of plumbing fixtures in the building and let the water demand calculator calculate for you what the estimated demand is. Same thing with fixtures, fixture branches and fixture supplies, except when you get down to just only one fixture, then the flow rate for one fixture branch and one fixture supply shall be the design flow rate of the fixture according to that table or according to the flow rate of that fixture that you're installing. This language is no different than what you're seeing in Appendix A already for continuous supply demand. You add it to your estimated flow rate. And then there are rows built in the calculator for other fixtures. And again, this language is similar to what you find in the footnote to the fixture unit table in Chapter 6. If there's a fixture not included in the calculator, you find a probability of use and flow rate that has a comparable probability of one that's already listed. And then all this is saying is that you will use the water demand calculator in conjunction with Appendix A procedures for pipe sizing. So basically, what this water demand calculator is doing is being an alternative to what's boxed in here. You're no longer going to be making reference to Hunter's curve or to fixture units. You're going to estimate the demand load using the calculator. The rest of Appendix A is the same, standard procedure as you would size a plumbing system that's for years, common engineering practices. But we're just looking at substituting the calculator for this. Do we have any questions? I know there was a lot of statistics, and that could put a lot of people asleep. Just residential. All right.
Dan, you said residential exclusively, right?
Yes.
Is there a limit to the fixtures? I mean, like 25, 30, 40, 50?
There is no limit.
Residence is huge.
Yeah.
There's no limit.
No. As long as it's a residential application.
So the commercial,
Not a hotel,
non-residential,
but an apartment, a large apartment complex. And we have an example of an apartment complex. So here's a small residential, one bathhouse, just for an example. On the upper left-hand corner, you have a bathroom group, just one water closet, one lavatory, one combination tub and shower. Then you have a kitchen sink with a dishwasher, you have a clothes washer, and then the building supply. So we're going to start with Appendix A rules. And according to Appendix A rules, you have to know what type of material you're dealing with. We're going to use L-copper as an example, and that will determine which chart to use in Appendix A. Chart A is for copper pipe. So these are just all for examples. So we have 45 psi available after the meter. We need a residual pressure of 20 psi. Calculate your head loss and other losses that you may have if you have a water softener for the residential dwelling. So anyways, all your friction losses or head losses you would calculate, and here's your available pressure for friction loss, 21.1 psi. And then using the longest run, your developed length, and this, for example, 113 feet, and an allowance for your fitting allowance. This is just a quick estimate, 25% of the developed length for fittings, and total developed length of feet is 141. Then to figure out your friction loss per 100 feet, you take 21.1, divide it by 141.25, multiply it by 100, and you come up with 15 psi. You need this information in order to use your Chart A. Up to this point, we're not using the calculator. These are just standard sizing procedures in Appendix A. So then you go to your chart, and at the bottom row is your friction loss per 100 feet. 15 is what we calculated. And then for the cold water supply, you run a vertical line and limited to 8 feet per second, our velocity. And then for each pipe size, you run a horizontal line to the right-hand side because that's your flow rate, your maximum flow rate per pipe size per velocity limitation. Again, this is nothing new. This is how we've always done it. So this is our exercise box here, 3/8 inch. And someone asked about 3/8 inch before. According to this chart, 3/8 inch will work up to approximately 2.2 gallons per minute. This was all well and good until, can you run 3/8 inch pipe to a tub and shower valve because the shower head's only running at 2 gallons per minute. And that's when the TC said, we need further experimentation before we like the idea of 3/8 pipe being used for a tub and shower valve. So that's why it's in the code that the minimum size is 1/2 inch, even though this chart and other charts would allow 3/8 inch piping. So for now, we're not considering 3/8 inch piping. So for 1/2 inch, 4.2 gallons is the maximum, 3/4 inch is 12 gallons per minute maximum, and 1 inch is 20. Now everyone is seeing where those values came from according to the chart. Now for the hot water, we're going to have a velocity limitation of 5 feet per second in this example. So still starting at 15 psi for your friction loss per 100 feet. You stop at 5 feet per second, and then you draw your horizontal lines accordingly to figure out your maximum flow rate. So for 1/2 inch is 3.5, 3/4, 7.5, 1 inch, 13 gallons per minute. Again, this is all preliminary information that you need before you use the water demand calculator. So we're going to be using this chart because once the calculator estimates the demand and flow rate, then you're going to know what size pipe to use. So here it is. Here's the calculator, and here's your diagram, the single family home. And we're going to start with pipe section 4, which is the building supply. All you do is enter the number of fixtures in column B. There's 1 clothes washer, 1 combination tub and shower, 1 dishwasher, 1 kitchen faucet, 1 lavatory faucet, 1 water closet. Total of 6 fixtures in this small example. Once you enter the number of plumbing fixtures in column B, you come over here and you just click Run Calculator. And the answer comes up here, 8.5 gallons per minute. So for pipe section 4, you have an estimated demand of 8.5 gallons per minute. For pipe section 3, which is going to be your hot water demand at the water heater, same thing, you enter in the number of plumbing fixtures that use hot water. The only one here that's eliminated is your water closet. It does not use hot water, so you do not enter the water closet in the calculator. So now you have 5 fixtures that use hot water. You click Run Water Demand Calculator, and here's your estimated demand at the water heater, 7.7 gallons per minute. Now for pipe section 2, which is your branch right here, you enter in the number of plumbing fixtures on a cold supply, and you have 1 combination tub and shower, 1 kitchen faucet, 1 lab faucet, and 1 water closet. 4 fixture, run water demand calculator, 7.7 gallons per minute. Very user-friendly. I mean, this is all you're doing is entering in the number of plumbing fixtures that's on the building supply or per branch that you're sizing. For the hot water, for branch number 2, it's the same thing. You enter the number of plumbing fixtures that use hot water. The water closet is excluded. 4 fixtures, click Run Water Demand Calculator, 7.0. And then you do the same thing for pipe section 1, which is 1 bathroom group. 7 gallons per minute for the cold, 5.5 gallons per minute for the hot. So now you have, in this small example, your estimated demand for every pipe section, every branch of the house. Now now you're going to size the pipe using your chart that you created earlier. So for 7 gallons per minute for cold, it's 3/4 piping. For 7.7 gallons for cold, pipe section 2, 3/4 piping. And for the building supply, 3/4 piping. Then you do the same thing for the hot. 5.5 gallons is 3/4 piping. 7.0 gallons per minute is 3/4 piping. 7.7 gallons per minute is 1 inch. Now notice that the pipe size increases because you're limited to 5 feet per second. If there was an 8 foot per second limitation, then this could remain 3/4 inch. But there's a velocity limitation of 5 feet per second. Smaller the pipe, the more friction loss. So you have to enlarge the pipe for less friction loss. So that's why that's increased to 1 inch. So now, as far as individual branches are concerned, like the individual branch to the water closet, the individual branch to the tub and shower, the individual branch to the lavatory, is all determined. You don't have to use a calculator for that. It's determined by the flow rate of the fixture. So kitchen faucet, 2.2 gallons per minute. You look at your chart, and you can run that on 1/2 inch. Clothes washer, 3.5 gallons per minute. You look at your chart, that can be 1/2 inch. Bathtub at 5.5 gallons per minute, 3/4 inch. So again, you don't have to use the calculator once you get down to the single individual fixture supply. It's just based on the flow rate of that fixture. Now this is the same example. We're just adding a new element, this continuous supply. We're going to add a hose bib, and we're going to add a landscape irrigation system. 10 gallons per minute is the flow rate of the highest zone. So we have our same information that we just calculated before, and this is the code language which says you have to add that continuous flow rate to your estimated demand. This is our estimated demand. The only thing it's going to affect is going to be the cold supply, because these are fed off of the cold supply, not the hot. So for pipe section 1, you have a hose bib, and say that hose bib is 2.5 gallons per minute. Well, you would add that to pipe section 1, and now the demand for that pipe section 1 is 9.5, and now the pipe size is going to be 3/4. Pipe section 2, again, you're adding this cold water hose bib. It increases the demand to 10.2 gallons per minute. Pipe size is 3/4 inch. Pipe section 4, would be the same thing, the hose bib. You have to add the hose bib all along that branch. And the demand would be 3/4. Now we have a new pipe section 5, which is before the landscape irrigation connection. Now we are adding landscape irrigation, 1 hose bib, 21 gallons per minute, and now the pipe size is increased to 1.25 inches. So that's how you would add the continuous demand in the scenario using the calculator. You wouldn't add continuous demand in the calculator. You would not use a calculator for that. You would add it to the estimate. Let's take a look at the PEX system. And what's different about this is now we have some branches that are supplying manifolds. Pipe section 3 and pipe section 4 are supplying manifolds. You would do the same thing again, your preliminary information. Here we are identifying PEX material. We can use Appendix I, figures 3 and 4 for our charts for PEX piping. And then some preliminary information that helps us estimate what the friction loss per 100 feet is. In this case, approximately 22 psi. And you would do the same thing with these sizing charts. Now in the PEX Appendix I, you can go a maximum of 10 feet per second on the cold. So we have a velocity limitation of 10 feet per second, and we're doing the same thing, filling in our sizing chart for 1/2 inch, for 3/4, 1 inch, 1.25 inches, derived from this chart. And then the hot supply is actually a separate figure in Appendix I for PEX, 8 feet limitation on PEX piping, and the same thing. You determine what your maximum flow rate is for each pipe size. So let's go to pipe section 1, and we're going to enter in all the number of plumbing fixtures. Again, look at your handout. It's easier to see than trying to look at this again. There's 11 fixtures, and you would list the number of fixtures. 2 water closets this time, 3 lavatories this time, and you would click Run Water Demand Calculator, estimates 9 gallons per minute. You have a hose bib, so you add that to your calculation. Pipe section 2, and we're not going to do every single one. Some of these I'll be giving to you. Same thing, pipe section 2, nothing different. In pipe section for the hot supply, you're just eliminating the water closets. Pipe section 3, that's a manifold. There's only 3 fixtures on that cold manifold. And you click Run Demand Water Calculator, 4.8 gallons per minute. I'm sorry, that's on the hot. But it's the same thing. You're just entering the number of plumbing fixtures per branch and finding out the estimated demand. Then you take this table, and again, you apply your earlier table to determine what your pipe sizes are. And for pipe section 1, the building supply is 1 inch. Pipe section 2, a branch, is 1 inch. To the manifold, pipe section 3 is 1/2 inch. Pipe section 4 is 3/4 to another manifold. Pipe section 5 is 3/4 inch. And then for the hot supply, 1 inch, 3/4, 3/4, 3/4. And again, for the individual, since these are manifolds, there are a number of individual fixture supplies going to the fixture. And again, the pipe sizing is based on the flow rate of those fixtures, and using your maximum demand for hot and cold, you select the proper pipe size for the individual supplies to the fixture.
On PEX, you have the ones that fit over the pipe, and you have the ones that insert into the pipe. The insert fitting is like 3/4 insert is actually only a 1/2 inch opening. This works both ways, or is there a different table depending on how you attach the PEX.
There is not a different table in Appendix I. It's based on the tubing size.
Okay, because like I said, 3/4 inch PEX with an insert is actually 1/2 inch through the insert. So would that make a difference where you maybe have a flow issue here?
Not according to the calculator. The calculator is going to estimate what the estimated demand is regardless of the type of material. But it's this right here that determines, based on your PSI, your friction loss, that's going to determine your pipe size. And there's
Okay.
no separate charts. There's nothing in Appendix I that will distinguish a chart using insert fitting versus an expansion.
So has anybody looked at that? Because it seems to me that the insert fittings restrict the flow and would reduce it, maybe Ed knows.
It does. But yeah, there's nothing to differentiate that in the sizing in the appendix.
Hi, to address the question of the PEX fittings, a study was done about 10 years ago by NEHB Research Center, comparing flow rates of PEX plumbing systems versus copper plumbing systems. And the PEX systems used in that study used the, what they call the crimp ring fittings, the F1807, smaller diameter crimp ring fittings, which you would think would choke down the flow somewhat, but it doesn't really because those fittings are just so short. They're only 1 inch long or 1 1/4 inch long or something like that. So it's just like when water flows through a quarter turn ball valve. The inside diameter of the ball valve is very narrow, but it's for a very short duration. So in the end, it really doesn't make much difference. So if you did follow what the suggestion was of having different sizing charts for cold expansion PEX fittings versus the non-expansion PEX fittings, it really wouldn't be worth it because you wouldn't see any difference. It'd probably be less than a 1% difference from one system to the other.
Thank you. Our last example, an 18-unit multifamily apartment. Just for a quick example, assume that each apartment dwelling is the same first example that we used. So we don't have to size these all over again. So each unit, just for the convenience of example, each unit has a estimated flow rate of 8.5 gallons per minute, according to our very first example that we used. And again, this is on your handout sheet as well, so you can see easier as we go along. So each riser is typical. Pipe section 1 at the very top is only supplying 1 unit at 8.5 gallons per minute. And then you would still put the number of plumbing fixtures for each unit. So for 2 units, you would double up the number of fixtures. Again, if these were all typical, you would just double up the number of plumbing fixtures. And the estimated flow rate is 11. For all 3 units on a riser, the estimated flow rate is 12. And here's an example of all 3 units. On one riser, you would enter in the total number of fixtures, 18, total number of fixtures, run water demand calculator, the predicted flow is 12 gallons per minute. So then as we start sizing each pipe section, the pipe section 4 is going to be the same as 3. There's nothing added to it. But when we get to pipe section 5, now we have 2 risers, estimated flow rate of 16.3. This shows the example of the whole building supply. There is 108 fixtures total. The estimated demand is 26.9 gallons per minute for the building supply for this apartment complex. Comparing the water demand calculator with table 610.4 in the UPC. Our example, our very first example, it's not going to be that big of a difference. It was a very small single 1-bath house. The UPC would estimate 13 fixture units with a building supply of 1 inch. The water demand calculator estimates 8.5 gallons per minute with a building supply of 3/4 inch, so it's a 1 pipe size reduction. In example number 2, where we saw the PEX system with the 2-bath home, The UPC would estimate 27 gallons per minute, building supply of 1.25 inches. The water demand calculator estimated 11.5 gallons per minute, a building supply of 1 inch, again, 1 pipe size reduction. And again, these are small single-family dwellings, but when you have a whole subdivision and you're adding up, it can be substantial. The biggest difference is when we look at the 18-unit building, and we're going to compare the water demand calculator with chart A in the UPC using Hunter's curve and fixture units. The UPC estimates 261 fixture units, which is approximately 77 gallons per minute. The building supply required would be 2.5 inch. The water demand calculator estimates 26.9 gallons per minute. The building supply 1.25 inch. You have 3 pipe size reduction, a 65% demand reduction. So I think we're answering the problem of oversizing systems using Hunter's curve by having the water efficiency fixtures accounted for, the correct probability of use in residential dwellings, and using methods in a calculator that will estimate the lower boundary as well as the upper boundary. And I think we've solved the problem. Questions now? We don't have actual field data. We have anecdotal data. In other words, we've looked at other studies that people have done and what the actual demand. There's an ASHRAE study that I looked at. The UK just published a study that they did on residential apartments, and I looked at what their measured actual demand flow was. We put the same number of plumbing fixtures in our calculator, and we were spot on, almost spot on, with the actual measured peak flows. Yes and no. The way we derived fixture p-values was from real data collected by Aquacraft. Aquacraft collected the residential end use of water survey. They created for us this huge database of over 1,000 homes, so we know what the probability of each fixture use is in residential applications. It's a huge database. And same thing with flow rates. So then once we have the probabilities, the fixture probabilities and flow rates from statistics, then we can use the equations in the calculator to estimate the probable demand, the peak demand.
Because I'm just questioning just that small of a, I mean, we had 1 inch come out of the water heater for that and 3/4 of the tub. I don't think you're gonna get there with chapter 6, so. I mean, we're getting smaller, it looks like we're getting smaller in the cold, bigger in the hot. Could that be true?
Well, understand that chapter 6 tables are a very simplified way of sizing. Appendix A is really a very accurate way of sizing pipe. If you want to stay within your velocity limitations and whatever your pressure losses is are calculated in that system, it's very calculated and very accurate versus using chapter 6 tables.